Recording in progress.
Yeah, come on, everyone. Let's start off. There. So last class we have done the pressure inside a solid sphere. There. So using a similar logic, let's try to get this. Let's say we have a hollow shell. So we have a uniformly charged shell with a charge density sigma. Sigma is your surface charge density. R is the radius. T is the thickness. And it is given radius is much greater than the thickness. So it's a very thin shell. The radius is much larger compared to this. B is your breaking stress. Now see, what is happening here is if you put the charge on the surface, every charge here will repel every other charge, isn't it? So all the charges on the shell are repelling each other. That means the shell is under expansion. Is that making sense? So the shell is repelling each other, but you're not letting them go away. So there is some kind of pressure on the shell. It's the first question. Find the pressure on the shell. So this is called as electrostatic pressure. That is the name for this. Because this pressure is generated because of electrostatic repulsion. We call this electrostatic pressure. Second thing, if you keep on putting more and more charge, the pressure will keep on increasing. At some point, the shell will explode. So find the maximum sigma so that shell doesn't break. And there we connected this to elasticity. Let's get this. For the A part, the result is really important. At least for a mains perspective, you should know the result. Let's see how to solve this. Give it a try. How do we approach this? Hope the question is clear. If you put a lot of charge on the shell will start repelling each other. This will generate a pressure on the surface. What is that pressure and what is the maximum charge you can keep on the surface? Maximum charge density. How do we even start? Listen, this thing, right? How do we approach this? You can't directly find the pressure. Let's take a shell with a small hole. So we are taking a shell with a small hole here. Now, if you take that hole again and if you add this back, I will get a full sphere. Now, I'll tell you what I'm trying to do. What I'm trying to do now, this shell is there. I'm trying to find the force due to this charge on this shell, this shell, this shell, this shell, this shell, everything. I will try to find the force due to the remaining shell on this small piece. And once I get this force, that force by this area should give me the pressure, isn't it? Now, how do I find the force due to the remaining shell on that? So I need to find the field basically. If I know electric field, I can get the force from field into charge. Now I can't do that directly. So consider 2 points. Let's say we have 1 point here, A just outside the hole and B just inside the hole. So A and B are very, very close, but they're just inside and just outside. So A is just outside the hole. It is on the surface, but just outside. B is just inside the hole. So A will be here for the patch. B will be here. A will be here and B will be here. Now, due to this entire shell, right, these charges will be repelling. You can see by symmetry, the field at point A will be outside. Let's call it E1. Agreed? Similarly, at B also, it will be E1. Why? Think about it. For all of them, they're on the same side, right? And A and B are very, very close. So they're almost at a negligible distance between them. So whatever is the field at A, B also will have same field. You guys agree? So this entire shell is pushing both A and B outside. So this point also will be E1 only. Great. Now for this guy, this small patch, this will be E2 and this will be E2. This will be opposite to each other. Why? This patch is like a small charge, isn't it? What will the positive charge do? It will push the field away from both the sides, isn't it? So here, E1 is the field due to the remaining shell, and this is what I actually want to find. At hole. E2 is the field due to that small patch. Now when I add this, at point A, the field will be E1 plus E2. At point B, the field will be E2 minus E1. Agreed? But now tell me one thing, what is the field inside of the hollow shell? Zero. So we know the field inside is zero. Therefore, this field EB, right? The net field inside the shell, E2 minus E1 must be zero. So we proved E1 is equal to E2. Now, all the story that we did is just to prove, right? This thing, see, it kind of makes sense. Think about it. If I take the full shell, the field inside is zero. That means if I cut the shell into two pieces, this left half and the right half are generating same field at the center. That's why they're canceling out, right? Now, the best part about this, even if you take an unsymmetrical piece, if you take this thing, this left half and this big right half are still canceling the field here. That's why it is zero. So if I can keep on doing this smaller and smaller, that means I can also say this small patch and this entire thing must be canceling the field everywhere. Just because of the argument, the total field is 0. That means you take any one piece and the remaining piece must cancel out the field due to that small piece. Is that making sense, everyone? And what about the field on the surface? So field on the surface is nothing but kq by 4 pi epsilon r square. But q by 4 pi r square is sigma by epsilon. This is nothing but E1 plus E2. But I already know E1 is equal to E2. Therefore, E1 is equal to E2 is equal to sigma by 2 epsilon. So we found out E1 and E2. Now, one mistake what people do, I'll tell you, see. They do like this. They will say field here is E, which is Q by 4 pi epsilon r square. Q by 4 pi r square is sigma. Then they will say field is E directly. Why can't I just take this field directly here? The problem with this is this field is due to this small patch and also due to this guy, isn't it? Now you tell me, if I'm trying to find the force on the small patch, can I take the field due to the small patch on myself? Are you getting the point? Whenever I ask you, find the force on the small patch, I should not take your own field on yourself, isn't it? I need to take the field due to the remaining people on you. But this field on the surface will give you the net electric field on the surface due to everyone on the surface. And we have proved this, and if you actually see, it is not a very small difference. We proved this, it is half of it, isn't it? Meaning on the patch, the field due to the remaining shell is sigma by 2 epsilon, and the patch itself is generating another sigma by 2 epsilon. So when I want the force on the patch, it should be the field due to the remaining shell into charge on the patch. I should not take the total field on the patch, because in the total field, there is a component, the field only due to itself, which should not be considered. Is that argument making sense, everyone? Just because of that one thing, you have to do all the story here. Any doubts on this page? Then, so we are done once we got that. So we have to take a small patch here. Let the area be A. Small area A. So the charge will be sigma into area. So I need to find this force. So this force on the small patch is the charge on the patch into the field due to remaining shell on the patch. You should not take the total field. So we will get force is equal to, this will be sigma into area, field due to the patch will be sigma by 2 epsilon. If you divide by force by area, we will get sigma square by 2 epsilon. There you can remember this result. So this turns out to be the electrostatic pressure. Quite a useful result. So this behaves just like a fluid pressure. Max doesn't care whether the pressure is coming due to charges or fluid, projected area. Every concept that you studied in fluid mechanics is valid. If you can apply projected area and all that stuff. So there, this would be a result. Should definitely remember the result for mains and bits, so they can ask a direct question. This is. We will prove this in Gauss law, but there is an extension of this. If you have taken a random shaped conductor, and if it has some charge density on the surface sigma, now this will be non-uniform. So this is valid only for conductors. The pressure on the surface will be sigma square by 2 epsilon. This is valid only for conductors. We will see this later on why this happens, because inside a conductor, the field is 0. So that's the thing we have to prove. We will prove that in Gauss law. But remember this result, quite useful. So what I proved here is only for a shell, isn't it? But if you take a conductor of any shape and any charge density, the field is sigma, pressure is sigma square by 2 epsilon. If sigma is changing, then the pressure also will change on every point on the surface. The question is still not over. Now, using this result, you have to do the second part. What is the second part? If you keep on putting the charge on this shell, at some point it explodes. Find the maximum sigma. Now you try. I'll give you a minute or two. And this second question we have done before. Any doubt so far? Please ask me on this. So this concept of pressure that we did right last class and today, this will again repeat in magnetism. We will call it magnetic pressure. This will again repeat in modern physics. We call it radiation pressure. So in physics, if you see, there are four types of pressure we deal with: fluid pressure, electrostatic pressure, magnetic pressure, and radiation pressure. So when light hits a surface, that also generates a pressure. And for all of them, the projected area concept works. So in case you have a problem with the projected area, you should definitely go and revise in fluid mechanics. Quite a useful thing, projected area and projected length. Projected length comes in, we saw in surface tension. This will again come in magnetic force. It will come in EMI. So this whole, the projector concept comes in almost 7 to 8 different parts. How do we do this? Second part of the question. And in case you forgot, let me show you where we did this. We did this in elasticity. Anyone remember this question? Exact same question. So inside it is filled with a gas. There is a hollow shell with thickness T, R, and breaking stress. Exact same question. And then they're asked you find the maximum pressure of the gas so that the shell will not break. And this is what we did. There, elasticity. We have done this question. Now instead of the gas ka pressure, we will use electrostatic pressure. So there, it is there in the notes. So how do you do the second part? So let's take half shell. It's a thin shell. So we have the pressure on the surface. And we know if the pressure is constant on a curved surface, we can directly use projected area. So this is the pressure, which is sigma square by 2 epsilon. So this will give you a force, sigma square by 2 epsilon into the projected area pi r square. All this force is acting on this thin cross section. This will be the tension. Do it now. Yeah. Try to get the angles and everything and do it. So from here we'll get tension. If you take a hemisphere, it is easy to get it. So tension will be that one, force, sigma square by 2 epsilon into pi r square. Now what is breaking stress? So breaking stress will be tension by area where the tension is acting, isn't it? Which area you're talking about? So that will be 2 pi r into thickness. Since the thickness is very small, I can treat that to be like a small rectangular strip. So done, they get this thing. So sigma square by 2 epsilon pi r square by 1 by 2 pi r t. So B is equal to sigma square, pi goes off, 1 r will be left out, 4 pi epsilon t. There from here you'll get sigma. pi nahi aayega. 4b epsilon t by r ka root. This is maximum. Anything more than this, the shell will crack. So only thing, replace the gas ka pressure due to electrostatic pressure and everything is same. You can take even a small point. You can even take a small area. But then you know how to calculate this projected area again?
So, but like, so we had done one tension inside a ring. So I was thinking we could take a 2D version of that and try to find the tension and equate that to
Yeah. Let me know once you get it.
horizontal.
Idea is not bad, but because if you take an half shell, I know all the values. Is this clear, everyone? This is how they'll ask a question in the exam. They will ask you the pressure and then they'll relate it to something else. I can even ask you something else. If it is a mains level question, imagine I have a soap bubble. S is the surface tension, R is the radius. Outside the pressure is P naught. Then what happened? Someone placed a charge on the surface, uniformly distributed it. Sigma. Now find the pressure inside. Remember the excess pressure formula? But now there is a charge on the surface. So find the pressure inside the soap bubble. Get this? I'll give you a minute. It's an easy one. Their questions will be like this. Once you got the pressure, you can literally bring everything. What is the answer? See. Now, what is the surface tension trying to do? It is trying to compress, isn't it? So P inside will be P naught plus 4S by R. This is the standard pressure. Now you tell me, if you put a charge, what are the charges trying to do? They're trying to repel each other. They're trying to expand the shell, so the pressure will decrease by how much? Minus sigma square by 2 epsilon. That's it. The soap bubble is trying to compress, so the pressure is increasing. The charges are trying to repel, so the pressure is decreasing. Is that clear, everyone? What if you put a negative charge? Then what will be the pressure? Will you get a plus? Gods, if you put a negative charge, they will still repel. You're talking as if you put a negative charge, negative and negative will attract. Whether you put a plus charge or a minus charge, the pressure will decrease. Clear with this thing? So the charge won't matter. Clear? Let's see one more. Let's do this in two parts. Let's say we have a sphere and we have a half sphere. You're getting it? So we have a half hemisphere and we have a full sphere. Common center. So let's say this guy is sigma 2 and radius is r2. This is sigma 1 and the radius is r1. Okay. So again, same story. So both have positive, positive, so they will repel. Find the force between them. I can take it as Q1, R1, Q2, R2 also. Same stuff. So this whole shell will be positive. This is also positive. So they're not going to keep quiet. They will repel each other. Yeah, both are hollow only. No? How can you put a solid? Both are hollow only. This is a hollow hemispherical shell. Hope the picture was clear. You have a full hollow sphere. Then you outside you have only half of it is covered with a hollow hemispherical shell. Both are positive charge, so they repel each other. So what is the force between them? Think. Take a minute or two. This is not the actual question. How do we do this? See, now, okay, sigma square. Let's see whether you got this thing. So what we will do, let's take a small patch here, a small patch. So due to this, right? So this guy is sigma 1, R1. This is sigma 2, R2. So the force on this small patch will be the charge on that small piece into the field due to the inside one. Agreed? So what is the field due to this thing? So the charge on the patch will be sigma 2 into the area A into the field will be, we know the formula, Q1 by 4 pi epsilon R2 square. I can get the charges. So Q1 is nothing but sigma 1 into 4 pi R1 square. Charge into surface area, right? Sigma into surface area will give you the charge. So this point is outside. Remember, this distance is R2. So the formula is KQ by R2 square. Sure. And what is this? This is sigma 2 into area. So this is the force. So if you divide force by area, I will get sigma 2 Q1. I can adjust this also. 4 pi, I will multiply r1 square and r1 square. This will become epsilon r2 square. That will become sigma 1, sigma 2, r1 square by 4 pi, pi is gone, epsilon r2 square. Is that clear, everyone? This is the what? This is the pressure on the surface. Clear? We are done then. Now, if you take this outer shell, now just now you proved this entire outer surface will have same pressure. It is constant. So the force will be how much? Pressure into projected area, which is pi r2 square. Substitute, which is sigma 1, sigma 2, r1 square. I'm missing one more pi here. It looks fine. So you'll get 1 pi here, and this will be epsilon. Check it out. This is the force on the outer shell. And by Newton's third law, this will be the same force acting on the inner sphere also. Did you see what it did? What did I do? I took a small patch. I found the force on that small patch and divided by area, got the pressure on the small patch. And once I did that, I got the pressure on the surface. Then I simply used the projected area. Makes your life easy. Neto, you literally have to take elements and then we have to integrate each element. Because the force will be in different directions, right? We have to take I cap, J cap, and then integrate. Projected area saves you time. Is this clear, everyone? Clear, Vihan? Here we are not taking sigma square by 2 epsilon. What are you talking?
So like last
The,
question, we have the pressure
the
one.
question is force between them, na?
Yes, sir.
Why
That's
are
what
you
I'm,
finding force on due to yourselves?
yes, that's what I'm trying to confirm it. We won't.
You're not taking that. वो तो internal force बन जाएगा ना. Those things will cancel. Clear? Now, the actual question is this. What if I have this hemisphere and this also have half of that and half of this? Able to visualize the diagram? This is getting overlapped. Common center. Let me use another color. Still looks the same, but okay. There is a common center there. So same story, sigma 1, R1, sigma 2, R2. Now find the force between them. Now, unfortunately, there is no symmetry also like the previous one. And you don't know the field due to an half shell. How do we approach this? Burona, Daksha.
Sir, in the previous question, the first part of this question, sir
Mhm.
actually tried to find the field at R2 due to the spherical shell.
That is
And
this only, no?
yes, sir.
Yeah.
So then I found the force on the hemispherical shell.
That is, how did you find the whole force together? You took the total charge into field.
Yes, sir.
You can't do that, right? So you're saying this force and this force direction, you will add them directly. देखो ना हर जगह force ऐसा है. How are you adding all these forces without taking components?
Okay.
Thought it.
Yes, sir.
That was a mistake. इसलिए जो double आएगा answer.
Yes, sir. I got twice. Yes.
Because you know you have a projected area pi r2 square, you must have taken 2 pi r2 square for that area. Because you have to take components, it won't work.
Okay.
How do you approach this thing? Listen, it is all based on symmetries. There's no need to actually solve, but you need the first particle result. Listen carefully what we're doing. So what I will do, I will take a full sphere, okay? And I'm going to take this small piece. Now, what is the force on this small piece due to the full sphere? 0. Because if we take a full sphere, E is 0. Therefore, the net force is 0. Agreed? So I can split this sphere into 2 pieces now. I will split this into this plus I'll split this into this, 2 halves, the big one. Now, in this big one, this chota sphere will look like this, the hemisphere. Agreed? Again, be careful. I'm not literally adding this and this. When I did this, someone was saying, sir, when you add these two, you'll get full sphere, and beach me, you'll get 2 double shells. I don't mean that. You're getting the point. We are just adding the forces between this half and the red one. This half and the red one must be equal to the force due to this full blue thing and the red one. Are you getting it? You're just finding the forces. Now, from this symmetry thing, so these two shells will repel each other. That would be this way. Let's call it F1. These two also will repel each other. This also will be F1. Why? Both have to be F1 because total force is 0, no? Do you guys agree? If I combine these two, I should get net force 0. Matlab, this repulsion is F1. This repulsion is also F1. Isn't this what I'm asking you to find in the question? So if I find F1, my job is done, right? Any doubts on this part? Then the second part, this time what I will do, I will take the inside one full and I will take this guy off. And this result I already know, isn't it? I know this result. This guy is F, which is this one, sigma 1, sigma 2, R1 square pi epsilon. This also can be split into 2 parts. I will take this small sphere half. I will take this small sphere half. Then you're trying to find the force on this guy. And then you're trying to find the force on this guy. Now, did you notice something here? This and this are same, isn't it? This and this are same. Yes. Then what will be the force on this thing? So due to this, let this force be F2. Let this force also be F2. Sorry, this is F1. This force is also F1. Is that clear, everyone? Then F1 plus F2 must be how much? This F. So from here we get 2, 1 is equal to F. Therefore, F1 will be half of this sigma 1, sigma 2, pi, R1 square by 2 epsilon. Is this clear, everyone? Think about this is complete symmetry, but you need to know the result of the first part. But once you got this, you can actually use symmetry. Again, what did I do? I took an half shell, I took a full shell. So then I said the full sphere I will divide into 2 pieces. Then the force due to this half big hemisphere and this half big hemisphere on the small one is equal and opposite because the net force was 0. So therefore I proved both the shapes have equal force F1 and F2. Even though they don't look similar, the force is equal. Then I took a small, inside sphere is full, outside is half. And then again, by same argument I showed you, this guy and this guy are same, and this guy and this guy are same. Be careful here. Here I am finding force on the smaller shell. Here I am finding force on the bigger shell. By Newton's third law, the forces will be opposite and equal. Right? And then, and if you can clearly see here, both are in the same direction. So F1 plus F2 must be equal to this F, and thus F I already know. And the best part about this question is, if I had given you a shape like this, keep them at an angle also, the answer won't change. So if you have taken this at an angle, the force will still remain same. Force between them will be this guy only. Sigma 1, sigma 2, pi r1 square by 2 epsilon, independent of theta. Again, you can prove it that symmetries. Is this clear? Good question. Next one. Clear, na, Daksha? But these are the kind of questions you'll get in advance. Next one. Then we have something called self-energy. So what is self-energy? Again, it is same as potential energy. Technically speaking, there is no difference. Meaning, think about this thing. How did we define potential energy? We said it is the energy between all charges. Now, if you take a shell, there is a positive, there is a positive, 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 positive. These two will have potential energy, these two will have potential energy, these two will have potential energy. Won't charges on the surface will interact with each other? So this is the potential energy between the charges on the system. You're getting it? So that's why we call it as a self-energy. So how we can define this? The amount of energy required to create a continuous charge distribution or assemble by bringing charges from infinity. Now, what do you mean by this thing? So listen to this thing. I'll show you one, then I'll ask you to prove for the solid sphere. Let's say I'm creating a hollow sphere. So initially, I have nothing here. There is no charge. So I wanted to create a shell on this place. So what did you start doing? From infinity, which is a very far, you're getting a small dq charge and you're putting it on the surface. You're distributing it on the surface. So you bring dq, 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 so on. When you bring dq, dq, the charges start accumulating on the surface. Let's say it has acquired q charge. Now you're continuously bringing dq charge. You're bringing again dq. Now listen to this. If you're bringing this dq charge, do you think this q will keep quiet? As you're bringing this dq charge, this charge will repel this thing, right? Means forcefully you have to bring the charge and put it on the surface. In this process, you're doing some work. So where does all this work go? So that work is getting stored in the form of potential energy. That means if you take a shell, all are positive charge, and let's say for some reason the shell explodes, all these charges will fly away because of repulsion. The kinetic energy gained by these particles must be equal to all the work done you did before, isn't it? So basically, when you're bringing charge onto the surface, every time you bring a charge, the charges which are already sitting there are repelling. You have to do work against them to put the charge there, and eventually, after putting dq, 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 let's say you have acquired q charge. So there we created a shell. So the question is, how much energy did I spend in creating this shell? That must be the energy stored. So this is how we do. Potential at infinity is 0. The potential in the shell is k q by r. So the work done by the external force will be charged into potential difference. So dq into v surface minus v infinity. So this much work you have to do every instant. So let me show it here. So dw will be dq, potential on the surface will be kq by r. So the more charge you bring, more repulsion you get, so more work you have to do. So this will be the work done by external force will be integral k by r integral q dq from 0 to r. So this comes out to be k q square, sorry, k q by capital Q, k q square by 2r. But we know work done by external force is nothing but change in potential energy plus change in kinetic energy. Since you're bringing the charges slowly, kinetic energy is 0. Therefore, you get the self energy. You should definitely mark up the results, kq square by 2r. This is the result. So if you have a shell of radius r and charge q, all the charges on the surface will interact with each other, generating this much energy. Means if the shell explodes, the kinetic energy of the system will be equal to this thing, kq square by 2r is half mv square. Clear, everyone? This is for a hollow shell. But everyone got the story what we did? Initially there was nothing. Then you brought dq, 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 and then you just ended up with plus q. So using the same logic, can you guys do for the solid sphere? So I have to create a solid sphere. Again, just to give an idea, initially there is no charge. Right? So wanted to create a solid sphere, there is nothing there. So you started bringing dq charges. Now be careful here, the sphere won't create it suddenly. Initially have nothing. You will create a small thing here. So radius bhi badega, charge bhi badega. So this will have plus q and radius small r. And then you bring dq, 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 dq. Eventually the sphere will become big. So here the charge is everywhere. This eventually becomes plus q and radius r. So unlike a shell, right, where you're putting charge on a radius r, here you have to increase the radius also. So every time you bring the charge, you are increasing the radius by a small dr. That is the difference between this and the hollow shell. Can you find the total work done or find the energy of this thing? So initially there was nothing. You bring dq, put it in the center. Next time when you bring dq, put it around it. Next dq, put it around it. So every time you're making a small shell and placing on top of it, like an onion, layer upon layer. Previous one was easy. The radius was always fixed. Now here the radius is also getting messed up. Try, I'll give it 2 minutes. Q दिया ना रे God. तो see ना. So every time you bring charge Q, how much is that? You can, if you want charge density, you can take it. That is not difficult. So what is dq? So if you bring your so this is the catch here. Previously dq was you're bringing small quantities, but here dq will also keep changing. So dq will be charge density rho into that volume, which is 4 pi r square dr. And what is rho? Rho is total charge by total volume, q by 4 by 3 pi r cube. Isn't that the rho? You're making a uniform charge sphere, right? Whatever is a rho for this must be the rho for this also. Is that clear, everyone? So that into 4 pi r square dr. 4 pi will cancel. You end up with 3q small r square dr by r cube. So this much charge you're bringing every time. And you're taking this charge and putting on the surface, and you're increasing the thickness by dr. I hope you're getting this. So you have to bring this much charge in order to increase the radius. I think you're done. Then the work done will be small work done will be this charge dq into potential at the surface minus potential at infinity. So charge into potential will give you the potential energy. So this guy will be 3q r square by r cube into dr, and the potential on the surface will be k small q by r. What is small q again? We need to get that also. What is small q? Small q is again rho into 4 by 3 pi small r cube. So this will be q into r cube by r cube. So substitute here. So this will be 3kq by r cube. 1 r will cancel. R dr q r cube by r cube. Perfect. So work done by external force. When you integrate this, we will get 3kq square by r power 6 integral r power 4 dr 0 to r. That will be r power 5 by 5. So that will be 3kq square by 5r. This is the work done by external force. This is equal to delta U plus kinetic energy. Therefore, the self energy for a solid sphere is 3kq square by 5r. Definitely mug up the results. So for a hollow shell, it is kq square by 2r. For the solid, this thing is 3kq square by 5r. Clear, everyone? Actually, you could have found q here and you could have differentiated to get dq. That also would have worked. So rho will be the final charge, meaning charge density, right? Total charge by total volume. All clear with this? Let's see a question how they'll use this. Let's say we have a hollow shell and we have another big hollow shell. Both are connected by a conducting wire. They're very far, so the shells don't interact with each other. This thing has a charge, let's say 2q. Radius is r. Let's say this thing has a charge minus q and 2r. Now, if I close the switch, charges will transfer between them. And something will happen, heat also will be produced. So find the final charges and the heat produced when switch is closed. Remember, this is an example I gave in conduction. If two conductors are connected, charge will transfer till the potential becomes same. Find final charges and heat produced when switch is closed. Hollow conducting shells, right? If that is solid, I will shade them, na? How do we do this thing? So if you close the switch, so some charge will transfer from here to here. Let us be small q. Right? So this guy will become 2q minus small q. This will become minus q plus q. So they can ask this question also. How much charge will flow through the switch? So let charge q flow from left to right. So the left side will become 2q minus q, right side will become minus q plus q. Then the potential of this shell V1 will be k into charge 2q minus q by radius. This potential V2 will be k minus q plus q by 2r. Since both are connected by a wire, potential has to be same, conducting. V1 is equal to V2. This will become k 2q minus small q by r is equal to k minus q plus small q by 2r. K and r will cancel. I'll get 2q minus q is equal to cross multiply 4q minus 2q is equal to minus q plus q. Q will be 5q by 3. So if I take this and substitute here, this will be q by 3 and this will be 2q by 3. There, that is your final charges. Clear. Then, now what is the initial system? Initially, there are like two shells here. So this was 2q and this was minus q. So the initial energy was k charge square by 2 times radius plus k charge square by 2 times radius. So be careful, iska radius 2r tha. So when you read out the formula, na, read it like that, k charge square by radius, 2 times radius. If you say 2r, it will be 2 times of 2r. So people do goof up sometimes. So this is the initial situation. Finally, the charge became q by 3 and this guy became 2q by 3. There, if you don't know self energy, you won't be able to solve this heat ka question. So here the final will be k q by 3 whole square by 2r plus k 2q by 3 whole square by 2 times 2r. There you got final minus initial. So what is the heat produced? Initially you had 100, finally you have 70. So the balance must be heat. U initial minus U final. Solve this, you'll get the answer. So without self energy, you can't solve the heat produced part. Clear with this? You know how else they can ask this question? If you guys remember this question in surface tension, anyone remembers this question? We have a soap bubble of radius r. Someone kept a pipe and they started blowing air and the radius became 2r. So in this, I will add one more thing. If I put a charge here, plus q. So now if I blow the soap bubble, this also will expand. What will change in the equation? Think, I'll give you 30 seconds. Same question, the soap bubble, if I kept a plus charge also on the surface, what will change additionally? If you remember how we did this in the first place. Think, take a minute. Fine, now let's charge. I didn't mean charge density record. So energy भी change होगा ना. Find the work done by external force. What will change in that? Hmm. Yeah, there is no interaction energy. There is self energy only. Interaction is between two different systems. Na? आएगा. That's the next thing we'll do. क्या change होगा question में? If you guys remember, what was the for this question? What was the answer normally? Change in surface energy plus work against atmosphere. Remember? Now you will get one more additional term: change in surface energy, self energy, isn't it? So initially radius was q and r, so self energy was kq square by 2r. Now this will become kq square by 2 times 2r. Is that making sense? You have to include that also now. So you're doing work against atmosphere, you're doing work against surface tension, you're also doing work with electrostatics. So total 3 terms आएगा इसमें: change in surface energy, work against atmosphere, plus the change in self energy. Clear with this? That's it. See, you need not make new questions and everything. Whatever you already did, उसमें add कर सकते हो. So that is how questions will be framed. Clear? Next one. Next one. Let's say we have a hollow shell plus q 2r. In that, let's say you kept a solid sphere plus q and radius are concentric. Find the total energy of the system. What do you mean by that? Find the total energy. Listen, what I'll tell you, what I'm asking you. Initially, there is nothing. Okay? I created a shell. Will this cost me some energy? I created a solid sphere. Will this cost me some energy? If I bring them closer, do you think they'll keep quiet? They will fight with each other. So I have to take it and put it inside. So that will cost me some energy. If I add all this, that shouldn't be the total energy, isn't it? You getting the question? To create them, I need energy, and to bring them closer, I need more energy. So if you add all this, that will be the total energy of the system. Think of like this: it's like you and your sister had a fight, and your mom is trying to take both of you to a function or something. So to take you both, your mom has to bribe each of you individually. And then after going to the function, so that you and your sister won't fight, she has to bribe again. Double bribe. Think of like that. The first bribe is to create each system. Second bribe is to make sure they don't fight. You have to bring them closer. So I don't know if you understood the analogy, but yeah. My mom never used to bribe. She used to take a stick and beat both of us. Problem solved. Let's get this. So give you an idea, right? There are two self energies and one interaction energy. Think. I'll give you a minute more. See, first let's create a solid sphere. So this guy will cost you, remember this is the self-energy, which is 3kq square by 5r. Then create this hollow sphere. Again, we are creating them at infinity, so they're not interacting with each other. So this is q and 2r. So this self-energy will be k q square 2 times that radius. Now what you're saying, I will keep the hollow shell here, which is plus q and 2r. So this is the solid sphere, which is at infinity. So you're planning to bring this and keep it in this spot, isn't it? And what is the potential inside the shell? So inside the shell will be kq by 2r, and potential at infinity was 0. So you're bringing this full sphere right from 0 potential to this potential. So we call this thing interactional energy. So to bring it from infinity to here, I need to give charge of the shell, that is q, into v inside minus v infinity. So that will be q into kq by 2r. So this is your interaction energy. This much energy you have to provide in order to bring them closer. Then you're done. So the total energy will be the 2 self energies and 1 interaction energy. Is this clear, everyone? So when you ask the total energy, this is how you do it. So 2 self energies and 1 interaction energy. Any doubts on this? Clear? Take a break. Come back by 7 to we'll continue from here. Any doubts so far? Hi, Akshay.
Sir, the question that I had sent you, so why
Mhm.
can't we use the concept of center of charge?
Because the forces are not linear. kq by r square. How will you use center of charge? The field on one shell due to another shell is how much? kq by r square. 1 by r square is not a linear function.
So
If you want to use center of charge, you need a linear function. इस क्वेश्चन में क्यों यूज किया तूने? Because यहाँ पे field was linear r bar.
okay, okay.
Okay, come back in 10 minutes. Yeah, sure. Switch on everyone. One of your senior just called up actually. Uska told you na, uska UG exam and CET clash ho raha hai. Both came on the same day. Did I tell you? It happened for 3 people. 19 they have UG exam. This is for Triple IT Hyderabad, and 19 they also CET. Same day, same slot. So UG people said they won't change. उनका तो एक ही day था. So we requested CET people, and then they're like, I think for 2 of them they adjusted on 21st. So that's what they called, and they're informing. I said, good, good. Anyways, so they have their own problems. Next thing. So there we got the self energy. So if you remember, right, hollow sphere and solid sphere, the formulas for the field, potential, and self energy. These are the important ones. The next thing, relation between field and potential. So we know field is nothing but force per unit charge, and potential is nothing but energy per unit charge. So end of the day, I'm asking you find the relation between force and energy, if I have to put it in layman terms. So it comes from here. So we know dW is equal to minus du. This comes from work per energy. Work done by internal conservative forces is equal to negative of change in potential energy. So work done will be nothing but F bar dot dr bar. This is nothing but charge into potential difference. So this will be Q into E bar force dot dr is minus Q into dV. QQ will cancel. We end up with E bar dot dr bar will be minus dV. So now, if I write this in the integral form, if I integrate on both sides, I'll get VA minus VB is equal to minus integral E bar dot dr. Quite a useful thing. This is an integral form. If I give you electric field and if I ask you potential difference, we have to use this formula. So E bar can be written as minus dV by dr. So if you write this in a differential form, this will be minus dou V by dou X. I hope everyone remember the partial differentiation. Minus dou V by dou Y. And minus dou V by dou Z K cap. This is your differential form. So if I give you potential and ask you for field, I'll use this thing. Quite a useful one. I think you can note them down. So these are the two relations between field and potential. One is a differential form and one is an integral form. Now here, if you observe, there is something about the minus sign. This is again another important statement. What does the negative sign indicate? The negative sign indicates in the direction of the field. If you travel in the direction of the electric field, the potential decreases. What do you mean by that? See, I'll just give you an example, crude example. See, let's say we have a river flowing. The river is flowing from here to here. So let's say you made a weird contraption. You made a small raft here. This is connected to a pulley here. And let's say this is connected to a block here. So as this raft is getting dragged by the river, this block will start going up. Agreed? So let me ask you this thing. If I leave this raft here, point A, or if leave the raft here at point B, from which point can I extract more energy? Or from which point can I pull this block more distance? A or B? A, right? If I leave from A, I can travel more distance compared to B. That means as you go along the river, the amount of energy you can extract will keep decreasing, isn't it? Does that make sense? The more you go down the river, the lesser distance you can travel further, isn't it? You're exhausting the potential energy. So something like that. So electric field is kind of like a river ka flow. the more you go along the river, the less energy you can get. So the less potential you can extract from the system. Logically सोचो ना, if you go to infinity, potential कितना हो जाएगा? Zero, right? So if you keep on following the field line till infinity, eventually your potential will drop down to zero level. Is that making sense? Something like that. So keep that in mind. So field is like something like a river, and if you go in that direction, your potential will eventually drop. So if someone gives you a question like this, so if you have 2 points here, A and B, can you tell me which one is more, field at A and field at B? And they'll ask you like this, compare field at A and field at B. Compare potential at A and potential at B. This will be a proper mains level question. Which is bigger, field and potential? This you have done before if you remember. What is field ka definition? Number of lines per unit area. Right? Maybe I should have reversed the arrows. I should have reversed the arrows. Wait. Now, so at point A, you can see the number of lines are same, but the area is bigger. So field at B is greater than B, but the potential at A is greater than B. If you go along the field lines, potential will decrease. So when you go from A to B, the field lines are going. So A ka potential is more. But point A, the number of field lines per unit area are less. So it's more area. So the field is less. Is that example clear, everyone? That's a proper mains level question. They'll just give that picture and they'll ask you this thing. EA greater than EB, VA greater than VB, EA less than VB, VA less than VB, and so on. 4 options they'll make. Any doubts on this? Clear? Let's see some questions. Hope everyone remembers partial differentiation. In case you forgot, I think the first time we did that was in work power energy. That is the only place we did so far. Let's see. So I give you potential xy square plus yz square. So this they'll give you potential. Find the field at 1, 1, 1. Find the electric field at the point 1, 1, 1. Let's get this. Remember, if you do dou v by dou x, only x is a variable, remaining are constant. So that's how you differentiate. Let's see. So first thing, dou v by dou x will be, x is a variable, everything else is constant. So this guy will be y square. Dou v by dou z, dou y by dou y will be x into y square ka differential is 2y. Z square is constant, dou y by dou y is 1. Dou v by dou z will be xy square when there is no z, so that will be 0. Yz square means z is a variable, so y will come out and that will be 2z. Is that clear, everyone? How we're doing partial differentiation? So when you differentiate a function, if you're differentiating with x, x is a variable, everything else is constant. So therefore, the field E will be minus dou v by dou x I cap minus dou v by dou y j cap minus dou v by dou z k cap. Substitute here. So this guy will be minus y square I cap minus 2xy plus z square j cap minus 2yz k cap. Now substitute 1, 1, 1, and you will get minus I cap minus 3j cap and minus 2k cap. Is that clear, everyone? Easy? Next one. Next one. Another way of asking the same thing. So we have a potential versus x graph, potential versus y graph, potential versus z graph. Now let's say this is 45, this is 30, this is 60. So they'll give you like this. The potential with x, y, z are three graphs given. Find the field in the region. How will you do this? Yeah. So what is this thing here? Basically, is the slope. The slope in the dy by graph will be dou y by dou x, which is tan 45. So you can directly do field E is equal to minus dou v by dou x I cap. So that's the slope in Vx graph. Dou v by dou y, slope in Vy graph. Slope in Vz graph. So this guy will be minus tan 45 I cap. This will be minus tan minus 30 j cap minus tan minus 60 k cap minus I cap plus 1 by root 3 j cap plus root 3 k cap. Clear. Clear, everyone? So that's it. You just need to take the slopes. So if I give you V, you can find the field like this. Now the other way around. So A is 1, comma 1, B is 2, comma 3. So if the electric field in the region is xi cap plus yj cap, if electric field in the region is y square I cap plus 2xyj cap, find the potential difference between A and B. Now it is other way. You have to use the integral form. Now I'm giving you the field and asking the potential difference. Let me show you one. We have done something similar like this in work per energy if you remember. Force is given, displacement, and then has to find the work done. So first of all, what is R bar? R bar is xi cap plus yj cap plus zk cap. So what is dr bar? Dxi cap plus dyj cap plus dzk cap. So what is the potential difference? So VA minus VB is minus integral E bar dot dr. So the dot product of this is minus. So if you do the dot product, you will get x into dx minus y into dy. So remember, you're going VA minus VB, meaning A is final, B is initial. So this guy limits will go from xb, which is 2, you're going to xa, which is 1. This is yb, which is 3, you're going to ya, which is 1. That is the thing. Be careful with the limits. VA minus VB, A is final, B is initial. So integrate this, minus x square by 2, limits 1 to 2, minus y square by 2, limits 1 to 3. 3 by 2, 8 by 2, 11 by 2 volts. That's how we do this. Clear, everyone? There'll be two answers, 11 by 2 and minus 11 by 2. So we have to be careful with the limits. Same thing, if I do the B part, then what will happen? Now can you try the B part? Try. I'll give you a minute. Let's see. So if you do the same stuff here, VA minus VB, when you integrate this, you will end up with y square dx minus integral 2xy dy. You can't integrate this directly because y is a variable, x is a variable. Y square dx I can't integrate if you don't tell me what is y as function of x. Then remember I told you, when this happens, there is something there. If you go back to work per energy, how did you deal with these kind of functions? There was a name for this. Anyone remembers? Remember what we call them? Perfect differentials. Look at this thing, same numbers, 1 comma 1, 2 comma 3, x comma I cap. So something similar. There it was work done, here it is the potential difference. So this is how we write a perfect differential. If you can make that into one single term, it's called a perfect differential. So this can be written as VA minus VB minus, this is y square dx plus 2xy dy. Now, if you can clearly observe that this thing is nothing but integral d of xy square, isn't it? Differentiate xy square, you'll get the same function. This is called a perfect differential. If there are two terms and if you can mix them into one single term, it's called a perfect differential. And perfect differentials are also conservative forces, remember? If a function becomes a perfect differential of force, it is a conservative force. Then how do we do this? So we can just take this, put xy square is equal to, put it as a new term t. So xa Ya square will be Ta, which is 1, xb yb square will be 2 into 9, that will be 18. So the simply integration becomes Va minus Vb is integral minus dt. Limits will go from Tb, which is 18, to Ta, which is 1. This is 17 volts. This is how you integrate these kind of functions. Remember, physics mate is pretty straightforward. Either you give me y in terms of x, give me a relation, I will do it. If you can't give me a relation, it has to be perfect differential, or else I can't solve the question. Now in this question, I didn't give you what is the relation between y and x. I simply said you're going from 1, 1 to 2, 3. I didn't even tell you how you're going. Then there's only one possibility. It's a perfect differential, because you can't solve any other way. Now, these are the things, the textbooks won't teach you these things. But when you solve and when you see these kind of things, you should realize next time when you go to the exam, you see something like this, it will click immediately. Boss, ये तो perfect differential होना चाहिए. I don't even care what is the question. Is this clear, everyone? Let's see one more. Any doubts on this? You should definitely check out the work per energy thing. We have more examples of perfect differentials there. That will help you a lot. We have an infinite line charge. This would be an easy means one. We have a point A here, we have a point B here. Let this distance be R1 and let this distance be R2. Find Va minus Vb. So there are 2 points in presence of a infinite line charge. What is the potential difference between A and B? What to do? What is the field here? The field due to an infinite line charge is 2k lambda by r. So Va minus Vb is minus integral 2k lambda by r into dr. A is final, B is initial. So this is R2 to R1. This will be minus 2k lambda ln r. Limits will go from R1 to R2. 2k lambda ln R2 by R1. Easy. But you should know the field due to infinite line charge and you should know this relation and you're done. Next one. So we have some relations here. Let's say in a region, field is 0, potential is also 0. Field is 0, but potential is not 0. Field is not 0, but potential is 0. Field is not 0 and potential is also not 0. So between these 4 statements, which of the following are possible? Means you can put whatever charge you want, however you want, do anything you want. Which of the following are possible? Just give it a try. What do you guys think? All are possible. See, E0, V0. That is easy, right? Put nothing. E0, V not 0. Take a hollow shell. Inside the hollow shell, what is the field? 0. But what is the potential? KQ by R. That is also right. E not 0, but V is 0. If you put a plus Q charge and a minus Q charge, at the center, what is the field? At the center, field is not 0, but potential is 0. Because plus Q will push, minus Q will attract. So field will be this. This is also right. This is anyway right. The problem with this thing now, most people think this way. E is equal to minus dV by dr. So they think if V is 0, E must be 0. You're forgetting V and dV are not same. V and dV are not the same thing. For example, see, let's say potential is minus 1, 0, plus 1. Is dV 0 here? Is dV 0 here? V can be 0, but dV not 0. Don't get confused between V and dV. So the full question is this actually. E0, dV0, E0, dV not 0, EV not 0, dV 0, E not 0, dV not 0. So now it would matter. So when you say E is minus dV by dr, if E is 0, dV has to be 0. V need not be 0. Don't get confused with that. V can be 0, but there is no compulsion it has to be 0. The mistake is this. People think V and dV are same. They're not. So going from that argument, this is fine, this is wrong, this is wrong, and this is wrong. Clear? I hope you're getting it, the difference. V0, dV0 are completely two different things. Next one. Any doubts on this? Arush, clear with this? Soham, Vignajit, Surya, Nikhil. Next one. Kritik, got this? Niharika, clear? Falak, Ahana, Puroja, great. Next one. Equipotential surface. Look at that word. The word is self-explanatory. Equipotential, meaning the surface where the potential is same everywhere. So the surface or a region where the potential is same throughout. right? So if I take examples of this, let's say if I take a hollow shell, plus Q and radius R. So if you look at inside, the potential is constant KQ by R. This is equipotential region. Now, if you go outside, you will find concentric shells. If you take this shell at a distance R1, the potential will be KQ by R1. So any point on this shell will have same potential. So this entire shell is equipotential. From here, if I take one more shell at a different distance, this guy will be KQ by R2. So every shell, right now, all shells don't have same potential, but each shell will have same potential. So here, the concentric shells are equipotential surfaces. So basically, the surface or the region where the potential is same is called equipotential surface. So for a hollow shell or a solid sphere, even for a point charge, the concentric shells are equipotential. Suppose if I take a infinite line charge, so here the equipotential surfaces will be cylinders. So this entire cylinder will have same potential. So here all the coaxial cylinders are equipotential. Suppose if you have plus Q and minus Q, can tell me where is the equipotential surface? This entire plane in the center, isn't it? The perpendicular bisector plane. If you take this perpendicular bisector plane, the entire plane, now look at this. If you choose any point here, they're equidistant. So that potential will be KQ by R, this will be minus KQ by R. Potential will be 0. Isn't it? That entire plane in the middle will have 0 potential. That's an equipotential plane. So like this, depending on the system, you can find the point or the locus of that curve where the potential is same throughout. But that is an equipotential surface. Yeah. Next thing. So what are the properties of this equipotential surface? First thing, since the potential is same everywhere, if you try to move on an equipotential thing, the work done is 0. That means if you are traveling on equipotential surface, you can travel without spending any energy. So this is one of the thing, what this NASA and everything they do, they use supercomputers, for what? They actually, it's very complex, right? There are multiple planets and multiple, orbits and all. They are trying to find an orbits. So if you want to go from A to B, and let's say if you can find an equipotential surface, something like this. So what these people do, they will take the satellite, they will enter this equipotential region, and they will try to travel along this line as close as possible. Then they'll take a detour. So from here to here, you can travel without spending any fuel. So you need to find as many paths as possible which are equipotential. So you can use minimal energy to go from one point to another point. I think there's a name for this thing. I think they call them Lagrangian planes or something like that. So the reason they use supercomputers is this, to figure out the orbits and everything. You can't do this manual calculations. So let's say you're sending from Earth to Jupiter or something. You need to take Mars ka gravity, Sun ka gravity, other planets ka gravity. It's a quite complex calculations. So you need supercomputers. Even then, it might take few days to calculate the orbits. So work done in moving a charge on equipotential surface is 0. Since potential difference is 0, because work done is charge into potential difference. Second thing, this is an important point. The electric field lines are always perpendicular to the equipotential surface. Why is that? Think about it. Suppose if you have an equipotential surface like this, and if you say there is a field E like this, so I can take a component here, E cos theta, which is the tangential component. We can take the perpendicular component, E perpendicular, which is E sin theta. Now, if you remember from the argument, in the direction of the field, potential decreases. So if the tangential component exists, suppose if E cos theta is there, that means along the tangent, the potential must change. So in the direction of E cos theta, potential changes. But you said it's an equipotential surface. Since it is equipotential surface, this is not possible. And there's only one possibility, E cos theta should not exist. Therefore, E cos theta is 0. Therefore, theta must be 90. Therefore, the field must be perpendicular to the equipotential surface. Is that making sense, everyone? Now, if you look at all the examples where I have drawn the field lines, you will notice the same thing. So if you take a point charge, how are the field lines? The field lines are coming out radially. How are the equipotential surfaces? They are concentric shells. There you can clearly see they're perpendicular. Similarly, this example also, if you remember plus q and minus q, if you actually draw the field lines, you'll notice now if you draw the equipotential surface here exactly in the center, isn't this perpendicular? You can prove that with Coulomb's law also. Dekho na, plus q minus q. If you take a bisector here, this plus q will push the field this way. This minus q will attract the field this way. The resultant will be this way. It is perpendicular to the bisector. And now if you go back to this beginning, starting when I drew this thing and we didn't even start. You guys remember this? Did you see what did I do here? I draw perpendiculars here. We will discuss this later on in Gauss law. A conductor is equipotential surface and the entire conductor will have same potential. So when the field lines enter a conductor, they have to enter perpendicularly and leave perpendicularly. And now Vihan, dekho, ye argument tha na? In the direction of the field, potential changes. So if you have a field line coming from this to this, you are saying the potential here and here is different. So a conductor cannot have two different potentials inside. So those kind of field lines won't exist. Are you getting this argument now? So you can't get field lines like this. So that this was the statement that in the direction of the field, potential changes. So there are some examples. Third one, the equipotential surfaces cannot cross each other. Why? Same argument. At the point of intersection, you will get two directions again. Because you said the field is perpendicular. For this surface, the field is this way. For this surface, field is this way. We can't have two directions. So therefore, you can't have two equipotential surfaces crossing each other. Yeah, these are the main three properties there. Clear, everyone? Let's see a question. Any doubt so far? This is a good question. Just now I taught you this and I'll just contradict again. Let's get this. Look at the question. We have two charges, Q1 and Q2, and this 8-color shape, this thing is an equipotential surface. Now, these things you can't manually draw them, you have to use a PC. But they have given this. And they're asking what is the distance between the charges with this information. So this equipotential surface ka voltage is 900, Q1 is 4 nanocoulomb, Q2 is 1 nanocoulomb. Find the distance between the charges, and this thing is an equipotential surface. And just now I made a statement, equipotential surfaces cannot cross each other. And they're crossing. So what? Try, I'll give you a minute. Now listen, you said you can't cross, and now you are saying they will cross. And what was the problem? We'll go back to the initial statement. What was the problem with the cross? You have two directions of field. So now you're indirectly telling me, boss, at that point you have two directions of field. How is that possible? Which vector can have two directions? A null vector. That point is a null point. That is the only possibility, isn't it? That's what you have to take a conclusion from that. The thing was, if they cross, they have two directions, right? So, but if you still insist they're crossing, then there's only one possibility. You have a vector there with undefined direction or two directions. That is a null vector. Zero vector can have any direction you want. So at the point of intersection, there are two directions of field. That must be a null point. It must be a null point. So at this point, E is 0. You're done then. So let this distance be R1, let this distance be R2. So the field will be KQ1 by R1 square must be equal to KQ2 by R2 square. This is equation 1. Second equation, potential KQ1 by R1 plus KQ2 by R2 must be equal to 900. This is the second equation. You'll get R1, R2 from here. R1 plus R2 is the distance between them, and you're done. Is that clear, everyone? There. So that is how you argue that. They won't cross, but if they cross, that must be null point. Next one. Vihan.
Sir, like, how do we know, like, net electrostatic potential V? So, sir, that is going to be same.
What are you
So
talking
that
about?
net
It's an
electrostatic potential. So can you hear me?
Yeah, I
Net
can hear you.
electrostatic potential. They're talking about that surface only.
Right.
Okay, so just wanted to confirm.
तो क्या कंफर्म ये तो लिखा है फोर्थ स्टेटमेंट देखो ना पढ़ो ना एग्जाम में who will come and confirm the question for you have some trust on your reading ability, right? Next thing. So let's say we have some equipotential surfaces. So we have concentric shells. So this potential is 60 volt, 10 centimeter. This potential is 30 volt, 20 centimeter. This potential is 20 volt and 30 centimeter. Like this, three equipotential cells are given. So using this information, tell me the direction of the field and the value of the field. Find E bar. These are HCV questions. So these are again three equipotential surfaces, parallel surfaces. These angles are 30 degrees, 30 degrees, 30 degrees. So this is 40 volt, 30 volt, 20 volt, and 10 volt, and so on. This point is 10 centimeter, comma 0. This point is 20 centimeter, comma 0. This point is 30 centimeter, comma 0. So these are plane equipotential surfaces. So using these pictures, you have to tell me what is the field in the region. Can you see some kind of sequence in the first one? V into R is constant. Meaning there are two ways you can guess this. See, first of all, these kind of potentials can be created by what? A point charge or a shell or a solid sphere, isn't it? इतना तो guess कर सकते हो. So if you notice here, you will observe V into R is how much? 60 into 0.1 is 6, isn't it? Check karo, 30 into 0.2 is 6, 20 into 0.3 is 6. So we get here V is equal to 6 by R. So you can say this is equal to KQ by R, and then you're done. So field is equal to KQ by R square. That is 6 by R square. There, that is a field in the region. Or you can even do E is equal to minus dV by dr. You will get the same thing. So the important thing is to realize V into R is constant. And then what about the direction of the field? Now we know the field lines will be radially away, but which way? Are they going in or coming out? Again, remember the statement, in the direction of the field, the potential decreases. What is the potential? 60, 30, 20. It is decreasing, right? So field lines must be going away. Are you getting how we did that? So the important thing is to understand there's a sequence V into R is constant. Then you'll get it. What about the B part then? Can you tell me what is the direction of field in the B part? It should be perpendicular to these green lines, na? Which way? Up or down? In the direction of the field, the potential decreases. 40, 30, 20, 10. So it is going this way, isn't it? Is that making sense, everyone? How to get the direction? And then how do you find the field? Field is nothing but minus delta V by delta R. I can do this because it's a linear thing. So this will be the perpendicular distance. That will be how much? 5 centimeters. So delta V will be 40 minus 30 by the perpendicular distance between the, this is the perpendicular distance between the planes. So that will be 10 by 5 centimeter will be 100 there. So that will be 200 volt per meter. That's your field magnitude, everyone. Clear with this? The potential difference between two planes by distance between the planes, right? Which is the perpendicular distance. You can't take 10 centimeters. Easy? So this is how they'll ask questions. Either they'll give you the shape and they'll ask you the field, right? Relation between E and V and all this stuff. So that this is one part of it, relation between field and potential. Exact same stuff is there in gravitation. Nothing will change. Even the alphabets are same, E and V. So gravimetry is the exact same stuff. So after this, we're left out with one concept called dipole. We will do that on Thursday, and I think we could wrap up early. If that finishes early, we'll start off with gravitation. We'll start off with gravitation ka intro also on Thursday. Okay, we almost did 45 questions. We're almost at the tail end of the chapter, so you can start solving the material, whatever you're solving. In case you are solving something, start doing it. Thursday we'll wrap up the chapter. We'll start with gravitation. Gravitation will look exactly same like the starting part, field, potential, ideas are all same. So you will see some duplication of problems also, but I will try to take some different ones. In satellites, in gravitation, the most important one is satellites, which we don't have it here. We will focus more on that. So gravitation also will not take much time. I think we will wrap up that also by next week. So both of the chapters will get over back to back. Okay, with that, we'll wrap up for that day. So if you have any doubts, anything, you can stay back and ask, or else you're free to leave. I'll see you on Thursday at 5:30 as usual.
Sir, in the last question.